Yesterday, we learned about the operational amplifier-based integrator, a circuit that performed integration, and we also learned that the integrator acts as a low-pass filter. Today, we're going to look at a different circuit known as a differentiator using an op-amp. It consists of an operational amplifier connected in negative feedback, which forces the input terminals to be equal to one another. So the inverting terminal sees the same ground that the non-inverting terminal sees due to the virtual short at the input. We do the analysis the same way that we did for the integrator. We note that the current flowing through C1, IC, has to be equal to the current flowing through the resistor, IR. We know that the current flowing through a capacitor is equal to C times the derivative of the voltage across the capacitor. We know that the current flowing through a resistor is equal to the voltage difference across the resistor divided by the resistance. Rearranging this equation, we can write that VO is equal to minus RC times dVi by dt. In other words, the output voltage is a derivative of the input voltage with some RC product multiplier. Examining this in the frequency domain, this is the time domain equation. We can see, remember, the impedance for a capacitor is equal to 1 divided by I times 2 times pi times the frequency times R, times C. I'm going to make a substitution and call I times 2 pi F a variable that we'll call S. This variable S is proportional to frequency. So we can rewrite this as 1 divided by S times C. Recall, impedance of a resistor is simply the resistance. Doing the analysis in a similar fashion, we will set IC equal to IR. So we can say VI minus 0 divided by 1 divided by SC is equal to 0 minus VO divided by R. Rearranging this, we can say that VO is equal to minus S times R times C. Interestingly, in the frequency domain, S is equivalent to a derivative in the time domain. So we know that VO is equal to S times RC times VI, or our gain, V out divided by Vn, is equal to S minus S times R times C. So if we were to plot this function versus the log of the frequency domain. And knowing that S increases proportionally with frequency, we would see that at S is equal to 0, or DC, the voltage gain would be equal to 0. And we can prove that this increases with a slope of 20 dBs per 10-fold increase in frequency, or what we call a decade. We don't need to know exactly what a decade is right now. We just know that the voltage gain starts at 0 and it increases with frequency. So this is what we would call a high-pass filter. And the reason we call it a high-pass filter is it blocks low frequencies and allows high frequencies to pass. If you recall, so this is a high-pass filter. If you recall, with the integrator that we looked at yesterday, it had a response that looked like this. The integrator allowed low frequencies to pass and blocked high frequencies. So today we'll be looking at the dual of the low-pass filter, namely the high-pass filter. So we can say that an integrator is a low-pass filter, and a differentiator is a high-pass filter. Relating this to your mathematical classes, when you do an integral is essentially doing an averaging operation, and averaging operations are low-pass filters. And your differentiator is finding the slope of the function that you're inputting to it. So when you take a derivative, you're providing a high-pass filter. We'll build the circuit tomorrow and measure its performance and see what the high-pass filter does to an audio signal.